Yeah, yeah. Okay. Good morning. My name is Jussi Lindgren, and um, actually, I have finished my PhD in applied mathematics here at Aalto University. So this is a familiar place for me. I live nearby in Helsinki, just some 5 kilometers away, and uh, I think it's a great opportunity for all of us that the society has decided to keep its hold its conference here at Aalto University. And I hope you guys will also have time to enjoy Finland and Helsinki and the sites. Unfortunately, the weather is getting a bit colder, I guess, according to the forecast, but it should be still quite okay. And also, thanks for Anders and Martin and others for arranging this conference. So my presentation actually is a kind of a follow-up on a paper we published, I think, 3 years ago within the preceding series of this conference. 3 years ago, I guess, yeah. And it was about Maxwell's equations. I mean, as probably all of you know, that there are quite a number of approaches that one can sort of derive Maxwell's equations, and I think it's quite interesting for me, sort of, to really understand how what these equations in a way mean. I think it was Richard Feynman who once said that electromagnetism is didactically, in a way, it's taught the wrong way. That one should always consider the electromagnetic force potential and not the fields, not the electric or magnetic fields as such. So at least he thought that the force potential is more fundamental than the fields themselves. Of course, when it comes to engineering and so forth, the fields are of enormous practical use. To me, it seems that well, along with relativity, quantum mechanics, and the foundation of quantum mechanics, I think electromagnetism is one of the deepest theories in theoretical physics. So it's always been a sort of personal interest for me to try to gain some insight what's going on without I don't know, without any sort of plan to have any useful theory as such, but just to gain insight, the intellectual insight, what's going on with electromagnetism. And my presentation is actually it's purely classical, so no quantum stuff here. Although I guess there is some link between the force potential and quantum at the sort of more fundamental level, but I'm not going there here. I'm treating this framework as a sort of a purely classical, so just relativity really, and no quantum. So without any further ado, as the title says, I'm going to talk to you guys about the Lorentz force law, and sort of try to convince that it has something to do with the geodesics and the geodesic equation from differential geometry, and also trying to figure out what is electric charge at the sort of more fundamental level. This is a very preliminary stuff here, but I think that there's always been some kind of an aesthetic intuition that guides me, at least in my sort of physical thinking. So that I think there are lots of things in a way popping up when I try to, combine and try to find linkages between various, I don't know, mathematical concepts within electromagnetism and relativity. And this sort of intuition is, I guess, guiding me also here. But let's see. Yeah, so it's down, it's going right direction. Yes. Okay. So I I think the sort of basis here, which is already presented in the reference one, which was our paper from 2021. The idea is that I don't know if all of you are familiar with sort of with Misner's and Wheeler's work from 1950s, I think 1957 or so. So the whole idea that one should try to, in a way, geometricize everything so that all of things are, in a way, charges, masses, so forth, are just merely geometrical concepts in a way. This is almost kind of like a philosophical thing because I don't know what is anything at the very bottom level. I don't know. Maybe it's nothing. Because in a way, when I become older and also I've done some, I don't know, economics and finance research, I think that in a way, ultimately, we may need to sort of accept that science as such is it's a sort of an instrumental thing, not an ontological one. So we never know what's really what are things themselves as such, but what we can find useful models that we can use in applications and trying to make sense of this weird universe. So just trying to recast here what's in paper in reference one. So what was the framework there? So the framework was basically that a singular metric is constructed, which is the sort of, call it the autotensor product of the electromagnetic four potential, so just the four potential times itself. And then if you treat this formally as a metric tensor, so
you can use the pointer, for example,
this one.
Yeah, you can
Okay. Yeah. So here, I'm skipping this one here. So here, we're using this. I can also actually write it here. So one thinks in this way. And then this is just formal thinking because, of course, this is singular, so it's not mathematically rigorous such because it's not invertible and so forth. But you can always add, if you need to, you can add a constant, some sort of a constant term there, and you can make it non-singular, and it doesn't really affect the results. So this was the sort of starting point here, and then you can think of the C as, for example, the Minkowski metric. And then if you start thinking that, okay, what's going on, and you formally calculate using various just basic mathematical routines, you find the Ricci scalar. You actually find that the Ricci scalar, with some assumptions behind, is identical to the sort of classical Lagrangian of electrodynamics, so the Faraday tensor, and the stuff there. And then then if you consider the sort of Einstein action, Hilbert-Einstein action, I think, yeah, then the stationary condition is, of course, the Einstein field equation. And this, in a way, I treat it as a sort of a generalized set of Maxwell's equations. But then you find a particular solution, so you considered a Ricci flat manifold. Then you find out that the conditions just the two equations from Maxwell's equations. And then the other part come actually directly from the Bianchi identity. So you have the full set of four equations. And in a way, I'm not sure, but it sort of reminds me of the sort of vector calculus identities that you have the nice sort of dual thinking that in classical vector calculus you have the identities that the divergence of a curl vanishes, and then the curl of a gradient field vanishes as well. I think it's almost the same. So these are really just these conditions in a way that they're characterizing the optimality. And then this is the sort of what was already in the paper, and what was missing was the other side of electromagnetism, which is the Lorentz force law on top of the field equations. And this is what I'm trying to do here. And as I said, because the stationarity condition means the Einstein field equation is basically optimal curvature, if you will. And then I find that the Lorentz force law is actually has to do with geodesics. So just like in gravity, you have the field equation for the metric tensor, and then the test particle follows geodesics. So it's exactly the same setting here, which is, I think, it's quite nice. And then also, if you do some basic algebra, you actually find out that this Lorentz force law corresponds to a sort of optimization problem where, in a way, nature tries to achieve a minimal transfer of mass and charge across a path in the space-time. This is what it seems to be. Some kind of a, I don't know, transport problem or something like this. Yeah. So the mathematical challenge here, I think, concerns, it's not just my research, but I think it's a wider sort of problem is the charge. Because in a way, if you think about elementary charge, like if you think about, I don't know, protons, electrons, what are they? I mean, we consider them to be point charges, at least when you do undergrad physics and so forth. So mathematically, they would correspond to some sort of a singularity. I guess you could model them with Dirac delta functions or functions, distributions, and that's one point. Then you can sort of formally treat it also as a kind of a distribution, as taking an analogy from, let's say, hydrodynamics or other classical physics fields. So you have a distribution of charge across the space-time. But what we usually have, I mean, if you consider, I don't know, you put one atom in empty space, you don't have a distribution of charge. At least to me, you have a singularity, you have a point charge somewhere in the space-time. So in a way, if you consider one charge or a countable collection of charges across space-time, then you actually have a well, you don't have charge anywhere, almost surely, in the sense of measure theory, if you will. Yeah, but I mean, this is challenging, at least for me, because I really don't know what's the right way to do. But let's see what happens. And then, just to have some intuition, this is just to rehearse what was going on in the stuff we published. So analogies, I think analogical thinking is very powerful also in physical research, in theoretical physics. So what I think, this is just my understanding, that if you think about this, the theory of classical Einstein's gravity, and this just electromagnetism, these are the sort of correspondences I think exist. So the four potential is coupled or is married with the metric tensor, if you think about the geometry. And then the classical, as I said, Lagrangian electrodynamics is the Ricci scalar. The Einstein field equation corresponds to a generalized electrodynamic wave equation. So it has a wider set of solutions. This could be actually interesting follow-up research problem as well. And then you take the Ricci flatness, a special case, you get the other side of Maxwell's case, and Bianchi identity, you get rest. So no magnetic monopoles and so forth. And then the divergence seems to correspond to charge, electric charge, because there's a nice condition actually that what I assume in the earlier paper is that the forecurrent seems to be just the gradient of the divergence. So it's a conjecture, but it seems to me that if the model is to be complete in a way, then electric charge has to be actually related to the divergence, the covariant divergence of the four potential. So you can think of it, at least I visualize it in the sort of hydrodynamic way, or a vector calculus, even undergrad stuff. That if you consider divergence, then you have some vector field, and there's a sink. There's a sink for the four potential in a way, but of course we're in 4-dimensional space-time, and then the source or the sink is just the point charge in a way. This is the idea. And then there's some link I have with the other connection coefficients on top of the Ricci scalar, which seems to have something to do with the forecurrent terms. Well, yeah. And then the problem is that if you consider the presence of electric charge sort of as a I don't know, like a charge distribution in classical term, then you cannot really use anymore the Riemannian connection, because in general the covariant derivative of the metric tensor doesn't vanish always, which is the requirement for the metric compatible connection, so the classical Einstein connection, if you will. And this might not always be. Nevertheless, I used it in reference 1 because it's the sort of starting point. And then, of course, when one starts to extend, the sort of easiest way to extend is to consider the so-called Wild geometry. I think there was yesterday a nice talk on Wild geometry. So then you have this sort of eigenvalue condition in a way, where the covariant derivative corresponds to this eigenvalue equation here. So this is just the definition, and so it's a requirement. And then we don't really know as of yet. Hermann Weyl, when he tried to unify electromagnetism and gravity in 1918, I think, he thought that the phi function here is actually the four potential. But in this model, it's not the four potential, it's something else. But the structure is the same. Okay, and then we need to make this conjecture, and this is purely ad hoc. This is something which is needed so that the model closes in a way. It might be deep or not. I don't know. But this thing here must hold. So if rho is the charge distribution, and this is the differential of proper time, this invariant must correspond to this. So this is the thing you see in, for example, in the phase shift, and also when you derive Lorentz force law in classical field theory. So this must hold. This is an assumption. And then remembering that the metric tensor here is assumed to be this thing here, and then you do the math. So you solve for this, and you assume that this holds, and furthermore, you guess that the phi function here is the four velocity, and then you do the math, just really straightforward. This condition, so the Weyl condition, or the semi-metricity condition, leads to this. So the covariant divergence of the electromagnetic force potential is just the charge, which is just what I needed if I want the previous paper to hold or to be complete, because there, as I said earlier, therefore current has to be the gradient of the covariant divergence of the force potential. And this seems to hold exactly if these conditions hold. So here is just some math, just to to get the idea. I don't know, for most of you this might be familiar, but it's always good to rehearse. So this is the Weyl connection. Here's the Christoffel connection. So the Weyl connection and the Christoffel connection are related by this thing here. You have the Kronecker delta, and then if you remember that we assume this to hold identically, and also this one, then actually this thing here, which I called S, this thing here is just it just depends on the force potential and charge. So basically, the Weyl connection is the Christoffel connection plus something which depends on charge and the force potential. Yeah. So then I proceed, and I take just the geodesic equation as given, so that the directional derivative to the direction of the velocity or the tangent should vanish, and this holds for the Weyl connection as well. And then I just decompose it like this. You get this, and then you substitute. You take the ordinary Christoffel connection. You substitute this thing there. You have just the ordinary partial derivatives, the basic stuff for the Christoffel connection, and you get this set of conditions here. And we proceed. You collect terms, you do some algebra, blah, 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 rearrange terms. And then you see here that there are pluses and minuses and sort of commutator stuff. So you find out that the Christoffel connection actually basically consists of the Faraday tensor here, the F. So just a regular. And then you have the symmetric part, but you can drop it, because at least for the time being you can drop it. You can think that the gradient of the force potential is skew symmetric. I don't know whether it's safe, but here I've done it. And then you end up with this. So we had the geodesic equation, and you did the stuff I explained. You end up here, so you get this. And what is this? This is just the Lorentz force law, right? Plus some stuff which is related to the Weyl connection I explained, so it depends only on charge and the force potential. So there's some other stuff here. So you can call it, I call it the generalized Lorentz force law. And the extra term, just a wild guess, could have some relation with the Aharonov-Bohm effect, because if this is zero, there seems to be still a force, in a way, in the system acting on the charge, even though the electric and magnetic fields vanish. So there could be a connection. Yeah. So here, yeah. And then if you do, if you further require the sort of classical requirement of conservation of charge, so that the covariant divergence of the current vanishes, which comes from the Stokes law, I think, or the Gauss law, then then you end up with this, that the covariant Laplacian, or the Laplacian Beltrami, operator of the charge must vanish. So this charge density must be, I don't know, call it covariantly harmonic, because I mean this is of course a 4-dimensional extension to Laplace equations. So this demands, or this makes sure that charge is conserved. And I think yeah, and then what I told you earlier was indeed that now we have the sort of the model is closed, because now the covariant divergence of the forward potential with the gradient gives you exactly what is required in order that the Ricci scalar is the classical electrodynamic Lagrangian. Yeah, and then take a detour into classical field theory. So this is just the textbook derivation of the Lorentz force law in classical field theory. So this is the action, proper time here, and then you have the potential term, which is the inner product of the forward potential with the displacement. And remember that there was I can draw it here. There was the requirement that this holds by assumption. So this one is actually just transfer integral for the charge, right? So here is mass, here is charge. You end up with this. So the action is just this one. So this is charge. E is elementary charge here for as an example. I guess the square term is to take care for the fact that might be plus or minus. Yeah. So it seems to be that in classical field theory, if these assumptions which I require, if they hold, then the classical field theory of Lorentz force is just the interpretation is that nature wants to minimize the mass and charge transport, and the necessary condition is the Lorentz force law. And this thing here, I'm not an expert in all these things, but I think this animal here, it pops up in lots of places, and I think the key is here. Okay, then I try to just go through quickly some preliminary conclusions. So this was just the classical stuff. But then I mentioned also that there's a link to quantum mechanics. So the link might be that if, in a way, I think there was yesterday a talk on the sort of the fractional view of the space-time, or the fluctuating view of the space-time. Then if this is the structure of the space-time, these things fluctuate randomly as well, at least instrumentally speaking. Then what it means immediately that if this fluctuates, then you have actually random electric and magnetic fields, and you also have random charge popping up, because you have I mean, this is also, the divergence is also random. So, and this is just the charge. So in a way, if instrumentally speaking, if if you have the fractional or the stochastic interpretation of quantum mechanics or stochastic spacetime, whatever, then it seems to imply that at very small scales, positive and negative charges appear and disappear at very small scales because of this thing here. But this is just very preliminary. And here is one way to see it if you use math. So instead of a sort of a deterministic metric, whatever it be, you replace it with a sort of a stochastic metric where the epsilon is basically a random variable, and then you require something from it. You get the expectations, just the deterministic part, for example, with this structure. But this is also preliminary stuff. But I'm just trying to say that I think what is useful is try to combine the sort of deterministic structure of the space-time within this electromagnetic potential with the sort of instrumental stuff from quantum mechanics, because that would, in a way, explain a lot of things. And then some final remarks. So once again, this I just said, that charge can be sort of created by, if one can, as you remember, if there's a forward potential, and then there are electric and magnetic fields, and these are related. So if you can use and engineer electric and magnetic fields in such a way that you can create divergence for the forward potential, then you can basically create charge out of thin air. This is just this is just mathematics, but I guess it holds, because this thing here can be created with some right choice of electric and magnetic fields to create at least local divergence for the forward potential. But it's more for the engineers. and then again, charge is a kind of a sink with positive charge and vice versa with negative charge. And the random creation and annihilation of charges, as well as electric and magnetic fields, are expected if we have an interpretation of quantum mechanics that there's some, if we speak generally of vacuum fluctuations, if this thing fluctuates randomly, then you have this. This is just physical thinking. And as I said, this stuff is instrumental because I don't know what's going on. I mean, this is, I don't know what this thing is, but the math should predict all these things. Yeah, and then there's the old paper, and this is interesting. This is, I mean, I referred to already earlier from 1957, so it's quite interesting because there was the sort of complete research program manifestation. But I think I stop here in order to have some time for question comments. Thank you.